Okay, anything else before we get going? Okay. Any questions about anything? Okay, elimination reactions. We did the first one in class. I don't believe we did the second one, right? Key requirement for E2 elimination is the leaving group and the beta hydrogen that's being removed must be coplanar, with anti-coplanar being highly preferred. Syn-coplanar could work. Typically, anti-coplanar is what we'll be looking for. Because if anti-coplanar is possible, that's the way it's going to eliminate. We did the first one. Newman projection is recommended to see the relationship between the H and the leaving group. Let's do this again here. First off, substitution elimination. These reactions are hand in hand. They're mixed together. If you're looking at this fresh, is it substitution or elimination? Because we do have a tetrahedral carbon with a potential leaving group, and so we can do either substitution or elimination. Which is it? First off, is it unimolecular or bimolecular? Why bimolecular? We have a strong base / nucleophile. It's going to be bimolecular. Okay? That means it's either SN2 or E2. So which is it? E2. Why E2? It's a very sterically hindered base. There's no substitution on the oxygen, but right next door, lots of substitution. Okay? That really is detrimental to SN2. So instead of doing backside attack and kicking off the leaving group, instead it's going to take an H, which is much easier to do because the H is real small. But which H? Which beta hydrogen? We have beta hydrogen here. There's one there. We'll call that HA. There's actually two there, but I'm only indicating one of them because they're identical. Then there's one over here, and it has stereochemistry. And it's forward. That would be HB. Do we have another beta hydrogen? How many different possible alkenes can be obtained here, theoretically? 3. Double bond here, it's not stereogenic. Double bond here, it would be stereogenic. Because if you put double bond between this carbon and this carbon, that is, there it is, then on this carbon we have an ethyl, and on this carbon we have a methyl and an ethyl. Well, the ethyl can either be trans to that ethyl, or it can be cis to that ethyl. And high priority groups opposite, that would be what? E? Z? Okay? Or we can put the double bond in on the other side between that beta carbon and the carbon with the leaving group. Hold on, I was wrong. That alkene's stereogenic too. So the double bond here, we have the methyl, and then we can have this group. Right? But then this compound can also be like that, Z, E. There's actually 4 possible alkenes that we could show. Because in each case, they're stereoisomers. Which one of these 4 are we going to get? Well, what can we call these here? Some type of name. We can refer these to as what? Seitzelf, however you want to spell that. And these 2 would be called what? Why is that? Disubstituted, trisubstituted. So which product is this reaction going to give? Which is preferred thermodynamically? Seitzelf, right? When do you not get the Seitzelf but instead get the Hofmann? When the base is very sterically hindered, right? Is the base very sterically hindered?
Yes.
Yes. Why? Because HA is more accessible. HB is sort of hidden between 2 groups here. Or we could say HB is a tertiary CH, or HA is a secondary CH. Tertiary CHs are going to be more hidden. It'll be easier for this to take that. Okay, so if it's the Hofmann product, which Hofmann are we going to get? E or Z? Why E? What? Yeah, but remember the H in the leaving group need to be anticoplanar. Two H's here. Well, here's the take home for this. When there's 2 H's, you have a choice. You see up here, this H over here, which one did we eliminate? Over here? We eliminated that H. We only had 1 H. We had to rotate this to get it anticoplanar to the bromine. Here we've got 2 H's. Either one can be removed. You're going to have 2 Newman projections that work. Since you have a choice, you're going to get the best product. The best product would be which one? It would be this here. This is your Hofmann product. If that was the Hofmann. This question's difficult. Not difficult, it's a little vague. Because some instructors or some testing formats will actually want you to abstract HB. And they're going with, well, this is sterically hindered, that's why it's not doing substitution, but we're going to give the Is Tva product. The answer here is a little vague. That's why sometimes I'll ask you like this. I'll say, okay, show both products. Show the Hofmann and the Is Tva. Well, here's the Hofmann. Okay, now show the Is Tva product, if it was to be formed. Which of these will be formed?
Z.
E or Z?
Z.
Z? Why do you say Z?
Because you have to rotate to make the H anti.
In this case, we only have one H. That's the one that has to be abstracted. That one must be anti-coplanar here. We need to draw this in a Newman conformation to see this. I'm going to stand over here. Looking through here, I'll draw this as carbon 1 in the front, that's carbon 2 in the back. Front carbon, I see a methyl straight down. HB is coming towards you. If I'm over here, that's on my right. The ethyl group is going behind the board. If I'm over here, that's on my left. This is what I see. Okay, back carbon. I see a carbon with an ethyl going away. It's coming down from that carbon. That group and that group are eclipsed. It's coming down. Methyl, that's eclipsed with a methyl. I see a chlorine going up and to the right. That's eclipsed with that HB. And there's an undrawn H here going back. Which if I'm over here, back is to my left. So there's an H here. Got to be careful. This H is not a beta hydrogen. The H is on that's an alpha hydrogen. We're not abstracting that one. We're abstracting the HB and the chlorine. Right now they're syn coplanar. They're both like this. They're eclipsed. We need these to be anti-coplanar. Let's rotate. It doesn't matter front or back. Let's rotate the front. Let's put HB here. Put the ethyl here. And the methyl straight up. That's the front. The back did not change. There's an ethyl. There's an ethyl on the front and the back. We're dealing with the back. The back did not change. Chlorine here. And H here. Here's HB, here's the chlorine. Here's where you eliminate. Those are anti-coplanar. The base takes the H. The electrons move in between the two carbons. You can't see the two carbons. And kick off the chlorine, all in a concerted step. The two ethyls are on the same side. The H and the methyl are on the other side. Which one is it? Z. The two ethyls are on the same side of the alkene. Not the same end, the same side. And the H and the methyl are over here. Because when the concerted elimination takes place, those groups are fixed. And it takes place from that conformation because the H and the leaving group are anti-coplanar here. Okay, there's two possible Is Tva products, but the one you're going to get is the one circled. There's two possible Hofmann products, but the one you're going to get is circled, if you did Hofmann. Again, sometimes it's vague of which one to predict. The more sterically hindered the base is, which one's going to be favored? Hofmann. The question is, how sterically hindered is enough? We know the trend. Okay, we showed them both. Questions? Again, if there's two H's you're dealing with, you don't have to do this. Because if there was two H's on this carbon, for example, don't write this down. If there was another H here, it was HB prime, there was two, then you could show two good Newmans. I could show this one with this H anticoplanar, but then I could rotate it and put this one anticoplanar. And since you have a choice, you're going to go with the conformation that has the larger groups further away. And that's going to lead to the larger groups further away in the product. So if you have a choice, you're going to get the better one. If you do not have a choice, if there's only one H, you got to go through it systematically and you're going to get the only one you can. That's the only one you can, and it ends up being the two alpha groups are on the same side. Two alpha groups are on the same side. Okay, next one has a ring. What is TEA? Triethylamine, we saw it in the substitution handout. Sterically hindered nitrogen, because it's sterically hindered, it's not good doing substitution. Instead, it prefers to do elimination. Triethylamine is commonly used for E2 eliminations. All right, it's neutral, but it's an sp3 nitrogen, so we can consider it strong. It's not super strong, but it's strong enough to do an E2. THF is just a common solvent. We got a leaving group here. Beta hydrogen here is like this, HA. We did this one at the end of class. Did we do this one?
Yes.
Yes.
We did it, but it was at the very end. We didn't talk about it much. HA. I'm going to distinguish these two H's up here. There's two of them. Let's call that HB. I'll call that HC instead of B prime. Okay, what product we're going to get here? How sterically hindered is triethylamine? Very. Well, instead of ethyl groups, what if I made it isopropyl groups? Would that make it even more sterically hindered?
Yes.
Okay, so is triethylamine highly sterically hindered or not so highly? Again, that's the problem. How sterically hindered is it? Is it so sterically hindered that it's going to promote and give you the Hofmann product? Or is it okay and will it still give you the Is Tva product? That's where the vagueness comes in. All right? Again, I just erased the H's here. Is there something else that can help us here? Can this reaction even give the Is Tva product? Why not?
If it did the ethyl, that H is not anti the iodine.
By the way, Is Tva product would be putting double bond in here, yeah? Double bond here. Try substituted. The put the double bond in at the other position, it would be disubstituted. You guys got to make sure that you see that that's tetrahedral. We did nothing down there. It remains tetrahedral. We have stereochemistry. A lot of times you guys will draw the alkene and put the group like that. Once it becomes an alkene, it's now trigonal planar. Since it's planar, everything's in the plane. The group is now in the plane. Is Tva product. Will this reaction give the Is Tva product? The answer is no. Because the HA is not going to be transcoplanar to the leaving group. First off, it's not even trans, it's cis. We'll make this the ethyl, although it's an alkyne. The iodine, make it red. The H and the I are cis, correct? The red and blue are cis. Okay. The leaving group must be what? It must be axial. Because only when it's axial is a neighboring group going to be able to be anticoplanar. Which group is anticoplanar to the iodine? The ethyl. Okay, that's not an ethyl, but it's the group. This will never be, unless we switch it. If we do a ring flip, well, then no group is anticoplanar to the iodine. This H is not anticoplanar. Is there any H on the board that is? Any beta hydrogen that is? I can't remember. Bolded, was that H? HB? HC? Which hydrogen of the three can be anticoplanar to the iodine? HC. The one that's trans. And if I showed the one that's trans, we're going this way, the one that's trans is this one. And if that's straight up, you see how this one is straight down and it's anticoplanar? There's the plane right through here. They're anticoplanar. Not that one. That one, trans. The triethylamine, you take this H, these electrons move in here and kick that off all together now, and you get this product. But which H is going to remain? HB will remain. I'm going to draw that in there to clarify which H we took. And the one circle will definitely be the product here. There's no ambiguity, there's no vagueness, because in this case you cannot get the Is Tva. Because this H will never be anticoplanar. It can be syncoplanar. There it is. No, that's not it. The H was blue. Right there, syncoplanar. They're both up. Here's the plane. It can eliminate syncoplanar, but it ain't going to do that before transcoplanar, and transcoplanar is over here. There's transcoplanar. That's going to rule. That's going to govern. That's how it's going to go. Even though elimination over here gives you more substituted. Transcoplanar beats more substituted. Down below, which would react faster? A or B? Which would react faster? Well, you got to know that the iodine must be in what position to eliminate. We're showing elimination products, yeah? Mechanism is what? E1 or E2? Well, the base is strong, hydroxide, E2, yeah? Since it's E2, we got to have anticoplanar or syncoplanar, but anticoplanar highly preferred. Either one is only achieved if the leaving group is axial. The question is really this: in which starting material will the iodine be more likely axial? That's really the question. And this goes back to test 1, when we were doing conformations. Chair conformations. First compound. If we put the iodine axial, the tert-butyl will be here. I'm not going to worry about, let's put it here, we'll be right. With the iodine forward, this is on the left, up, oh, okay, it would be here. The iodine is here, the tert-butyl will be here, 1, 3, 1, 3, but will it be axial or equatorial? Or cis, to make this cis, it needs to be what? Yes, like that. That's A. If we draw B, with the iodine axial, tert-butyl is 1, 3. Trans here, for this to be trans, the tert-butyl needs to be what? Okay, this is B. Look at them. Which one is going to most likely be in this conformation? B. Because the tert-butyl's happy. What is A going to most likely want to do more than that compound? This is going to want to do a ring flip. And put both of these equatorial. And it's going to I'm staying here, I'm like this. But guess what? When this does a ring flip and exists like that, it can't eliminate. B is more likely going to have the iodine axial. B is more often ready to go. B is going to eliminate faster. Now note that the double bond can be put in down here, or it can be put in there, yeah? Both cases it's di-substituted, so it's going to be hard to tell which is going to be preferred. I just showed it being put in over on the right. But you could theoretically put the double bond in there, yeah? Beta hydrogens here. Back during test 1 in the workbook, there was a question. On page 9, during test 1, which constitutional isomer below will most readily exist with the bromine and a beta hydrogen in a trans-diaxial relationship? Trans-diaxial could also be said as trans-coplanar. Trans-diaxial will be coplanar. Why did I ask that question back in August and September? because I knew we'd be doing what we're doing today. Okay, from here out, a number of miscellaneous things in this handout. And again, we're going to merge substitution and elimination because they compete with each other. Double E2 elimination we did in lab. Why did it double eliminate? Why didn't it do a double substitution? Why didn't the hydroxide not just kick off the bromine and do a substitution? Hydroxide is not sterically hindered. I mean, that type of thing we need to start looking at. Some of these miscellaneous things address that. Okay. When either substitution or elimination is possible, which will occur? Factor number one, heat favors elimination. I think we may have mentioned this before. Due to entropy. If you take this compound and heat it in water, heat, higher heat better, it's probably going to do an E1 elimination. How do we know it's E1 and not E2? There's no strong base. Water's not a strong base, so it can't do E2. E2 requires a strong base. E1, what's the first step in this mechanism here? In-group leaves. Just going to make cation. Remember, that's the first step no matter if we're doing E1 or SN1. E1, SN1, same first step. At this point, though, the question is, will water add to the cation and get an alcohol product, which would be a substitution product, or will it eliminate and take a beta hydrogen? Well, heat favors elimination, and that means instead of it adding here, instead of it adding as a nucleophile, instead it takes an H, and these electrons move in. And that pathway gives that. And that alkene is not stereogenic, so we don't have to worry about it. Oh, by the way, why don't we take this beta hydrogen? There's one down there. Which one would you rather take? Call that HA, HB. If we took HB, the product would be is that it? Take HB, you'd get the Hofmann product. Question?
Why doesn't the carbocation shift? Or is that?
I was waiting for that. Yeah, good. Good. It could. You could show this mechanism with a shift.
Are the probabilities of a more stabilized alkenes favored over the carbocation shifting?
You're going to get the same alkene. Instead of the water doing something, I could just do a hydride shift. If I did a hydride shift, I would get that cation. That's good. Then you could come in and take this beta hydrogen and put the double bond in this way. It's the same product.
Okay.
But good. Good. This may actually be your preferred mechanism because the hydride shift is an internal mechanism where water coming in is external. That's going to be slower. Yeah. Good point. Which H are we going to take, A or B? Well, the product I showed, you take HA. Why not? Do we have to consider taking HB? Which product do you get when you do an E1 elimination? It was simple. Always give state cell. Always. Yeah, that's E1. If you're doing E1, you ain't going to get this product. Never by E1. When you do E1, taking the H, I was going to say it doesn't have to be anticoplanar. But actually it always is. Because this over here is planar. If that's planar, any H is going to be anticoplanar to it. It's almost not even applicable. The anticoplanar stuff is not applicable when you're taking an H in this from a carbocation. No, E1 always gives the best. Both of these H's are the same anticoplanarness to the cation, if you do a model and look at it. And so it's irrelevant. Okay, just remember your mechanism for E1. Because alternatively, if water attacked here, down here we're doing SN1, if water attacked there, oh, by the way, how did the OH get here? Because, it's going to do a hydride shift. So I should have taken the time to do that. Yeah, hydride shift, then the water attacks that cation, then you lose proton. Br can take the proton, hopefully you see the mechanism, and you get an overall substitution product, because the Br has been essentially replaced by the OH, even though it's on a different carbon. But which outcome is going to be favored here if we're heating? Heat favors elimination. Why? Because of entropy. And Gibbs free energy equation, heat magnifies which term? Entropy. First off, in which reaction is entropy favored? Elimination. Because elimination implies you're breaking, if you're eliminating, you're going to create a new molecule by elimination. See up here. Basically, water doesn't even react up here. It doesn't have to. If you exclude water, one molecule going to two. But down here, water does react, and so two going to two. 1 to 2 or 2 to 2. 1 to 2 is more entropy. It's more entropy. And by heating, you make that term become more predominant. And so the more you heat, the more the entropy is going to influence the reaction. Question?
So water doesn't even take the H in that reaction. Bromine does?
Up here?
Yeah.
Yeah, I showed it with the Br taking the H, the bromide taking. Okay, it's the same old thing here. How does HBr exist in water? As you learn in Gen Chem, it really exists like that, right? If water took the H, you would just be like that already. Okay? And actually, water taking the H is strictly more correct. It just depends on how somebody's going to show it. I've always sort of just reformed actual acids, even though we know they exist ionized in water. Okay, heat favors elimination. When you did double E2, did you heat or was that a room temperature? You heated, high reflux. Yeah, help favor elimination. There's other reasons that favor elimination. Number 2, involvement of a good nucleophile will favor substitution, while a poor nucleophile will typically favor elimination. Look at these examples. If you take this alcohol here, react with HBr, you're probably going to get a substitution. And thus it would be an SN1. by the way, on the quiz, Br minus, is that a strong or weak nucleophile? Br minus, strong or weak nucleophile? Why strong? I gotta be careful. I gotta be careful. I need to ask you. Br minus, strong or weak base? Okay, we said a lot of times anions and sp3 nitrogen, strong nucleophiles, strong bases, but not anions of conjugate strong acids. Okay? Br minus cannot be a strong base, even though it's an anion, because it's the conjugate base of HBr. If it was a strong base, that means it's coming back this way. But we know it doesn't come back this way. This exists like this. Anions of strong acids cannot be strong bases. So there are exceptions to general comments. But we're not talking about base here, we're talking about nucleophiles. If you do this reaction with HF, however, you will get elimination. Both of these have the same intermediate, this carbocation. Mechanism, strong acid, protonate. Then you ionize to make cation. Okay? These have the same initial step, forming the carbocation. The only difference is, like we did above, does the nucleophile add here and give a substitution product, or do we take a beta hydrogen and give a elimination product? Well, which is a better nucleophile, Br minus or F minus?
BR.
Better nucleophile. Better nucleophile is going to act as a nucleophile and add to the cation. All right, nucleophile. F minus is not a good nucleophile. Compared to Br, it's a worse nucleophile. So it's going to be less prone to acting as a nucleophile. Which is a better base? Actually, F minus is the better base, because it's less stable. And HF is a weaker acid. It's going to be more prone to acting as a base and taking a beta hydrogen and giving that mechanism. Okay? Better the nucleophile, the more it's going to want to act as a nucleophile. That is, add to the carbon. Because when the species takes the H, we call it a base. This is going to act as a nucleophile. That's more prone to acting as a base. All right? That brings us to this common reaction. A common reaction of alcohols is actually dehydrating them. That's what we did here. We essentially removed water. And HF was reformed. HF is the catalyst. Very common reaction. It's more common, though, to use sulfuric acid to dehydrate an alcohol. Because you protonate, this will, leaving group will leave, you'll be left with the cation. Yes, you could rearrange, or you can get here also. In this reaction, is there any nucleophile to attack this cation? The nucleophile is HSO4 minus. But it's really not a nucleophile. Have we ever had that attack anything? Act as a nucleophile? Never. Very bad nucleophile. Very bad nucleophile. So there's nothing that can attack the cation. Instead, well, we can use it as a base. We have used it as a base. Or you can use water. Something will just take the H and this moves in, and that's how you get the elimination product. Basically down here, there's no nucleophile. And anything can take an H in this fast step of the E1 elimination. And in the past, I've used probably the bisulfate anion to take the H. Common reaction. Overall, what have we done? We've removed water from the alcohol to make an alkene. Dehydration of an alcohol, very common reaction. Very common you use H2SO4 because there's no nucleophile. On the other hand, if we do this with HI, it's the same intermediate. Good nucleophile. And that's going to be more prone to acting as a nucleophile and giving you a substitution product. All right. So what have we done here? Got a good nucleophile, you're going to be more prone to having substitution. If the species is a terrible nucleophile, more likely to get elimination. And a common reaction is dehydration of an alcohol. By what mechanism did we do here? E1, using sulfuric acid because the conjugate base is a terrible nucleophile. And all it will do is eliminate. Okay, there's a couple of, well, there's a few more miscellaneous things here in this handout. We should have a quiz on Wednesday. Possibly Friday. I'll have to think about it. See which is best for us. Test on Monday.